now we go directly to the next speaker, Dr. Jun Tan. He is an expert in healthcare. He is a professor at University of Texas Southwestern Medical Center in the US. His research interests include translating research into clinical practice in radiation therapy, aiming at clinic work, efficiency improvement, and ensuring patient safety. So go ahead, Dr. Jun Tan.
How can I share my slides?
Yeah, share your slides.
I mean, how can I start sharing my slides?
Yeah, Jun, please, you will find a green button, share screen, on the bottom.
Oh, okay.
Please click with the right click of the mouse. Then you will find the different applications that you have already opened. So just open one of them.
Okay, I think I got it. Can everyone see my slides now?
Yes.
Okay, thank you so much. All right. Good afternoon, everyone. My name is Jun Tan. I'm happy I have this opportunity to share my experience of the AI's application in radiation therapy. I'm very thankful for Dr. Bouchard-Frost's invitation. He was my advisor when I was studying at Auckland University towards my PhD degree. It's very nice to see him and talking to him again. So the topic of this presentation is the AI watchdog for COVID-19, which is the application of AI in radiation therapy that are created to fight COVID-19. In this talk, I will first introduce the motivation and the clinical impact of this project. Then I will introduce the clinical implementation of this platform. I'll talk about our clinical work with and without this AI watchdog, and the AI model's role in this framework, and the result of our project. So starting from March of 2019, COVID-19 has become a huge threat to humans' life. And so of course, the best action is to detect people with COVID-19 as early as possible to prevent the spread of disease. And many publications have been shown that pneumonia due to COVID-19 can be detected and distinguished from that due to other disease by intercepting and analyzing simulation CT only. And there is not necessarily needed to use like tissue analysis, biometrics, CT images alone is sufficient enough to fulfill this task. The clinical impact that if we are successful in implementing such a framework, then we'll be able to detect to do the early detection of COVID-19 patients and prevent the spread of the disease, and the application to the similar scenarios in the radiation therapy department is also possible in the future if such scenarios happen again or for other tasks. In our department, the current clinical workflow is that the patient first needs to check in our front desk, and our nurses will do a consultation. They will take in the patient's vitals and ask them to sign a consent form. Then after they're done, we will send the patient to our CT simulation room, and then we will perform a volumetric scanning to get a 3D information of the tumors, locations, its size, and its spread. And we will also make sure that the patient is immobilized and the position is reproducible for the treatment. And when the CT images is ready, they are imported to our treatment planning system, and we'll have to determine the treatment technique, the radiation modality, beam arrangement, and we will calculate the dose, find out the optimal dose distribution, and evaluate the plan according to those lines and the dose volume history, etc., histogram, etc. After a plan is approved by the physician, we will do the plan QA, in which we will do the secondary dose calc to verify the plan is created correctly, and we will on the true treatment machine, we will perform the treatment process simulation, and we will measure the dose at points, and finally evaluate the plan quality, or whether the plan is passed a criteria by checking its gamma index passing rate. And finally, the patient will be treated using different modalities, either high energy photon or electron beams, or low dose X-rays, brachytherapy, etc. Sorry. Currently, artificial intelligence has been widely used in many stages of the treatment therapy, and the first step that people have tried is in the CT simulation scan, which is about the image acquisition. The major applications include the image reconstruction, image registration, and the simulation CT images from the MR image. The last one is extremely interesting. It's because in the treatment planning, we need to find the dose delivered to the patient, and this has to be done using the CT numbers. CT numbers is closely related to the tissue's electron density, but this information are not present in the MR images. MR images using magnetic resonance, but CT uses radiation. They are totally different modalities, but deep learning is just powerful enough that it can use the mutual information, and in numerous previous acquired CT and MR images to find their relationship, find the correlation, and is able to simulate the CT images from MR only, which means from MR only, we will still be able to get the electron density and be able to calculate dose without delivering extra radiation to the patient, which is of course is good for the patient's safety. The next popular applications of AI is in the planning phase. Also include the treatment technique, radiation modality selection, beam arrangement, and optimization. Also the dose distribution, prediction, and optimization. All these are actually active topics of that our group at UT Southwestern is working on. They have published many publications, and another application of AI is in treatment plan quality assurance. Usually, what we do is to deliver the real treatment plan on a lean lag, and if the treatment process is very long, this can take a long time. But then people's research shows that if we use machine learning, especially deep learning method, we can learn from the previous experience. We will be able to predict whether this QA will pass or not. So there is no need to perform the real plan delivery on a machine. Of course, it's an advantage. And this is still ongoing research in this area because many clinical physicists still don't trust this. They think, machine is out of our control. We will still need to do some physical measurement. Now I'm going to talk about our AI Watchdog project. What I have just shown is that the traditional workflow in our department, our Watchdog, of course, we don't want to interrupt the traditional workflow because people don't most people don't want to see change. They don't want to be interrupted. So our first goal is to monitoring the new CT images without our staff realizing that is something happens in the background. And then we'll pre-screen for the loss in those new CT images. If the loss shows that if the CT image contains loss, we can proceed to detect whether there is a COVID-19 or not. And if there is no loss in the CT images, then we can monitor in the next new CT images. So once the COVID-19 patient is detected, we'll notify the responsible party. So to monitoring the new CT images, the dosimetries import images to our treatment planning system, and the CT images are moved from the treatment planning system import folder. This process doesn't happen in a few seconds. It can be like 5 to 10 minutes, or sometimes even longer, depends on whether this dosimetrist is busy or he's working on something else, or when he will be notified that there is a new images. So they'll give us plenty of time to perform the initial checking. So the Watchdog copies a complete CT image sequence as soon as the patient scan is finished. Of course, this is much faster than what the dosimetrists can do. Then this Watchdog will check if the new images are coming from every. We check if the new images are coming from every few seconds, and when a sequence is complete, then it is copied to our AI Watchdog work folder. Because everything happens so fast, so there's no need to change our clinical workflow. People will not realize anything. The first step after we got the new CT images is to pre-screen the CT images for lungs. We check the CT images one by one. A threshold method is used. We used the empirical CT number, which is a -175 Hounsfield unit value. And across the region with CT numbers lower than the threshold and with area greater than 25 cm squared. And also the surrounding region must have CT number is greater than 175. Then we'll say, okay, there is lung detected on this threshold. So this we have to perform we have to detect whether there is COVID-19 on these patients or not. And if no lung is detected, then we wait for the next image scan. The AI module created for the detection of this of COVID-19 include the 3 parts. The first part is input. Input is just the CT scans of which lungs have been detected during the pre-screening stage, and will then predict whether there is COVID-19 or not. We train the model using 3 publicly available data sets and 4 different learning modules, and we use the Tensor workflow platform. The prediction is done on a GPU server, and the report will be reported in 3 probabilities: whether this patient is COVID-19, is common pneumonia, and normal patients. So the data for the AI module training include 3 data sets. One is from the China Consortium of Chest CT Investigation. The next 2 are both available on GitHub. They are COVID CT set and most metadata. The training of our model using 4 different data sets. One of them is only using the Chinese consortium, and then the second one use COVID CT set, and the next 2 use a combination of this data set. And the prediction result will be either COVID positive or COVID negative. And this is the confusion matrices for each of the training models on the tested set. Each row represents the data set that the model was trained on, and each column represents the data sets that the module was evaluated on. The labeling threshold used for each model is indicated on the lower left of each confusion matrix, which was fine-tuned from the validation data to maximize the trace of the confusion matrix of each respective category. These are the results using RC curves at different threshold levels, and each row represents the data set that the model was trained on, and each column represents the data set that the model was evaluated on. And we can see that using a combination of three different sets that give us the best result, which is shown on the top row. And once a COVID-19 patient is detected, we will notify the staffs. The recipients of the notification include the residents, physicians, therapists, nurses, and messages will be sent in either email or patient messages, depending on the urgency or the severity of the COVID-19 symptoms. And the information will include the patient ID and the prediction results. The platform for the development is a GPU server, which is a very high-end GPU server we got recently, and it use 192 gigabytes RAM, 2.5 terabytes hard drive, and we use Tesla GPU, 2 GPU cards. And the AI module was developed using CUDA 10.0 or 10.1 and TensorFlow 2.0. The results are, okay, the pre-screening is super fast. It's about 2 seconds. The prediction is 35 seconds on average, depending on the image volume size. And the result is reported in 3 numbers. Here's an example. A patient has a 64% possibility of being a COVID-19 patient and 35.9 possibility of having common pneumonia and 0.1 of a normal patient. So the conclusion, we have developed a watchdog for COVID-19 patients. The deep learning is used for detection of disease on city norms, and there is no alteration to current clinical workflow, and potentially it will prevent the spread of disease, and they can also potentially be applied to other scenarios. Recently, there are some interesting research in fighting COVID-19. The most interesting one I found is a recently publication from MIT. They performed a diagnosis using only cough recording, which can be an application in a patient check-in or consultation, which minimize the patient contact. And also 2 vaccines have been approved by FDA. The first one is Pfizer BioNet COVID-19 vaccine. It essentially makes our COVID-19 watchdog not critical. However, the idea of using highly accurate and efficient AI models seamlessly and with no change of the current workflow, and the stricter notification and action will be applied to other scenarios. So our model will still prove its usefulness in the future. The second vaccine is from Moderna's vaccine. It was just authorized 2 days ago. And this is a team for this project. I'm an assistant professor. I just graduated from a resident training half a year ago, and now I'm a faculty member. And the second person is Dan Wen. He's an assistant professor in the machine application in medicine and AI lab at Southwestern. He did most of the job in the deep learning model training in this project. And Dr. Yulong Yan, he's an associate professor and the computational physics director. He's an expert in computational science and its applications in medical physics. And then finally, Dr. Steve Zhang, he's a professor. He's the vice chair of the Department of Radiation Oncology and also the director of the medical physics division. He's also director of the MAIA lab. And okay, thank you so much. I'm happy to take any questions.
Thank you, Professor Jun, for your interesting talk. We have some questions for you. Adel Ulevki is asking, at what extent the use of 3D virtual reality to visualize the COVID-19 lesion?
Excuse me, can you repeat the question?
At what extent the use of 3D virtual reality to visualize the COVID-19 lesion?
Okay, the visualization of a COVID-19 patients is actually, okay, let me put it this way. We scan the patient in a volumetric imaging modality. However, all those investigations in the image features are checked on the 2D images because they show a pattern and that can be detected by the computer programs. And also those deep learning models, they perform the prediction, the training on 2D images as well. And of course, 3D can be used, but researchers have shown that 2D features is sufficient enough to achieve very high accuracy. So there's no need to do a 3D visualization and a 3D representation. I hope I have answered the question.
Okay. There's another question from Kamal Belulata. He's asking about the future of the application of this different neural network like CNN, RNN, in the retrieving or monitoring in medical images, especially for CT for COVID-19.
All right. In my opinion, what type of network you use is not critical. People have shown you can use CNN, RNN, or any type of deep learning models. And according to what I've seen on the archive.org, there are hundreds of papers coming every day. They all use different deep learning models. So the selection of a particular model is not a problem. It is how well you can tune your model to perform the best performance and how much data you can obtain. I mean, you can feed into your model. For example, initially we used only the Chinese consortium data. It performs really well. However, when we tested the training model on a different data set, for example, the data set that we in our department or data set from Russia, to perform the jobs quickly. Originally, it was greater than 95, 97, but jobs to around 70. Then we combined these models and retrain our model. Then the accuracy improved back to greater than 95. So which means model is not the key point. The data is what we should look for.
Also, Mohammed Zid Al-Abidin is asking about can dog watch be applied for patients with ARDS and sepsis? He means COVID-19 patients.
Okay, so AIA is okay. Yeah. Actually, you reminded me of one thing. I heard in one of our research meetings, people used the deep learning models on detecting AIDS. So I believe the question is already answered in the literature because people already did this research. It works, but I'm not so sure how well that their model works. Definitely, there is a solution for now. Only the only question is how accurate that model is and how well you can train the model is. So regarding the other application of this Watchdog, I believe it can be used for many different applications, not just the lungs, but also other regions. The reason we use it for lungs is because Here we have a patient intact every day, and it's critical to protect both the patients and the staff, and it's also critical to quickly notify any potential COVID-19 patients. And we have plenty of data for lungs. Lung is one of the major treatment sites in radiation therapy, and it can also be used in other regions, for example, the pelvis, brain. As long as there is any discernible traits on the images, it can be applied. Not only CT images, but also other modalities can be used. For example, MRI, which is very good at imaging soft tissue, and the PET image is good at physiology activities. Those are many applications. The power of this idea or this framework just need to be proved, but we are confident that once there is a chance, they will show its power. So actually, I believe it's the power of deep learning. Is there any more questions?
Khalid Lunas is wondering if there is a deep learning model that works efficiently and faster for such a task, and which doesn't consume GPU memory and make computing faster. It's this question.
Okay.
I know it's.
Yeah, I don't think that is possible. You know, the power of deep learning comes from two parts, right? One is the model itself, which is essentially a neural network. The other one is data. It's big data. As much as you can, you have to find all the free features you can use from tons of data. All those data requires high computation power, and which means you have to use GPU. And of course, if your data is not big enough, you can use a CPU high-end computer with like 8-core, 16-core CPUs. And if you don't care whether your task is time critical, for example, if it's okay for you to wait like 5 to 10 minutes.
Hi, John.
Not a big deal.
This is Jamal Bouchafra. Regarding the question of whether we can faster the model and the execution of the model, what we use in Google, actually, many researchers at Google and IBM are using currently what we call pre-trained models. Pre-trained models can help when the disease or the symptoms are very similar in some applications. And then the experience they got from one disease can be transferred to another one in order to go faster. And then they tweak the parameters for some differences that they may found. For example, between pneumonia and COVID-19, sometimes it's very difficult to discern between these two. And then many patients have been, you know, they have given the diagnosis was pneumonia, but it was not a pneumonia, it was a COVID-19 and vice versa. And then after time, they discovered COVID-19. Therefore, in this case, in order to speed up the process of the GPU resources, we might pre-train the model. Some people are pre-trained it, you can use it, but you can twinkle the parameters inside in order to fit the true model you are facing. Do you get me?
In my opinion, just to trick the parameters might not be the solution. What we do here is to retrain the model completely.
Can you hear me?
Yes, I can hear you.
Okay.
Okay, what I think is that retrain model probably is the best way. Just start from scratch, start the training from scratch, and by just tweaking parameters, probably I don't have a conclusion for now.
Can I add something regarding this point?
John, did you hear me?
Yes, I hear you.
Can I add something regarding this point? because we worked very recently in the last months on the detection of COVID-19, but by using ultrasound lung images. And what we did is to take different pre-trained architecture, in particular efficient net, and we tried to simply fine-tune with the data we have, considering different levels of gravity and so on. And we found out that indeed, so actually you don't need necessarily to train from scratch the architecture. You can fine-tune, but fine-tune up to a given level of the deep network. That is so not only the last layer, that is the prediction layer, but you have to go a little bit inside the network, disregarding the first layer. So the first layers, you may keep them, but only fine-tune the last layers. So, and it works. So it works actually.
Okay, that sounds interesting. I think we're going to try this idea, see if it can help us speed up the training process. Thanks.
June, the only condition is that an expert should be on top in order to, because it's part of a transfer learning. If you transform something to another task, that they have on condition that the tasks are alike or are similar. And this similarity sometimes can be difficult to see, you understand? So when something is apparent, then we pre-train definitely, because we don't train from scratch. Currently, we don't have time for that. But in condition that the two tasks are similar in some sense. See what I'm saying?
Okay, thank you. Are there any question, a general question on all the topics that we talked about? Okay, there is a question from Dr. Belahsen. He's asking, can this technique be reproducible or regenerated in other countries, knowing that the training, testing, and validation of your algorithms are based on specific data? Huh?
Is that a question for
John
me?
Tan, yes. To John Tan, yeah.
Okay, what was the question again? I didn't hear that.
Dr. Belahsen is asking, this technique, can this technique be reproducible or regenerated in other countries, knowing that the training, testing, and validation of your algorithms are based on specific data?
Oh, sure. Definitely, this technique can be reproduced or generated in other countries. What you only need to have is the deep learning model and the data. And the deep learning model we use is publicly, both the model and the data we use are publicly available. For example, the Chinese consortium is published in a Nature paper, and they share their data, their code, and you can download it from their website directly. And there are two data sets from are both from GitHub. I'm not so sure if GitHub is accessible from all of the other countries, but definitely you can download it from them, and there are detailed instructions on the explanations on how to use them, how to use their model. It's not just data, but also their models to use them. And for our particular model, we used a publication that we use the method used by the Chinese consortium paper, which is published on Nature. If anybody interested, you can let me know, and I will be able to share this paper with you. And also, you can also reproduce what we do here.
Any other questions? Okay, I think no question. We are at the end of on the webinar, and we would like to thank all the organizers, the participants, and all of those who interacted with us, and other webinars will be organized by CDTA in the next future. This will close our webinar, and thank you again for your participation.
Participants
Okay.
and the audience.
Goodbye.
Thanks to you again
Goodbye.
for having organized these webinars.
Thank you.
Thanks.
Thank you.
Goodbye.
Goodbye.
Goodbye.